Alright, so yesterday we left off at with the start of chapter 6. So we're chapter 6 looks into entanglement at a greater detail. So we learned that there are factorable states, which can be factored into product states, and there are non-factorable states, which by definition cannot be put into product states. So, for example, we have this Bell state here. These two qubits are entangled. This cannot be factored. Therefore, measuring in either of these two states, so measuring in a non-entangled state, measuring one qubit, measuring a single qubit, measuring a single qubit in a non-entangled state doesn't affect other qubit states. And the opposite is true for entangled states. So if we measure a given qubit in a fully entangled state, then in an entangled state, then we will affect the measurement outcome of others. For entangled states, measurement impacts all entangled qubits, not just the qubit being measured. All right. So we have there's different types of entanglement. We can have maximal entanglement, and we can have partial entanglement. So, for example, with the state that we were looking at there, these both qubits are entangled with each other. So the one measurement of one qubit will affect the outcome of the other. It doesn't matter which qubit we measure, it will affect the other qubit. So this is maximal entanglement. So the four maximally entangled states, I'll just go ahead and erase here, are our Bell states. So plus, which is 1 over square root of 2, 0, 0, state 0, 0 plus state 1, 1. Oh Lord. Okay. Minus, which is equivalent to 1 over square root of 2, 0, 0, minus 1, 1. We have a candelabra plus, which is 1 over square root of 2, state 0, 1, plus state 1, 0. and candelabra minus, which is 0, 1, minus 1, 0. So this is, all 4 of these are maximally entangled, our Bell states. Measurement of any one of these qubits will cause the other qubit to collapse to some certain value. However, we can also have partial entanglement. So with partial entanglement, this example they give us right here, cannot be factored into product states, but so it is entangled. However, if we measure the left qubit first, then we get state 0 with probability 3/4. 0 with probability 3/4. We have the 2 amplitudes here, so it's just 2 over square root of 3, 2 square root of 2, or pardon me, this is our norm square here, which gives us 2 over 3, or 2 times the absolute value of 3, 4 times 2, which is 8. So we have 2 over 6/8, 2 over, we bring the 2 through and get 6/8, so 3/4. Similarly, if we measure for 0, we wind up with did I miswrite this? No, I did not. Okay. So we have 3 over 4 plus, which gives us 3 over 16 plus 1/16, which is 1/4. 4/16 is 1/4. And our states will collapse to 0, and then an equal chance of being in 0 or 1 for the second. Whereas with state 1, if we measure 1 in the first qubit, the state collapses to square root of 3 over 2, 0 plus 1/2, 1, for the second qubit. So we have the ability to measure both. However, and they are entangled, but the right qubit collapses to these two sides here, So the right cubit, we might get 0 or 1 with a 50% probability. 50% probability of 1 for the second cubit. However, if we measure 1, we will get 0 or 1 with a 25% 25%. 0 or 1. So even though the left cubit, measuring the left cubit, did redefine our next qubit state, it wasn't completely deterministic because we had a probability for 0 or 1 for the second qubit. Second qubit. Instead of a deterministic outcome. So up here in our maximally entangled states, we can see that measuring in 0 or 1 for the left qubit dictates with 100% probability the outcome for the second qubit, whereas in a partially entangled state, it alters the probability of the second qubit's measurement, but it doesn't determine it. Probability is not equal 100% for the outcome of the second qubit. So that's partial entanglement. We do have entanglement, but it's not complete 100%. It's not maximal entanglement. So let's look at Oh, for the second qubit? Okay, so we can work through that. So right. For this. Okay. Okay. Yeah. So basically, so it's related to how when we were talking about measuring in our basis 0 and 1. If we want to measure, so let's say we take our, let me make sure that I do this properly. Okay, so we have so we want to get from our original superposition right here to 1 over 2, 0 plus 1/2, 1. So with probability 1/4, which is the amplitudes of our measuring 1, we go to, so essentially what we can do is we can rewrite this in the terms of our basis states. So we can say we had 3/4, 1/4, so we can say square root of 3 over 2 plus 1/2 1, or sorry, 0. So this is the psi form of the measurement of our original equation in the the original superposition, but this is the original superposition rewritten for a single qubit. So we take our one. Sorry, let me scroll here. So measuring 1 occurs in 3/16. So the original amplitudes for 1, 0, and 1, 1, 1/4. And then we can measure, and then we have 1. Oh, I see. Okay. So the amplitude for, okay, yeah, so right. So it's 3 times as much. So when we collapse into the state, right, we would have plus square root of 3, 0 plus state 1. This has to be normalized. So we would bring in a 1/2. Okay. To normalize everything. That's 1/2. I assume that's where they're getting that from, because we have this is our probability. This is our probability within the superposition of getting this exact outcome of 1 and then 1 and then 0. So first we have a 75% probability of getting into this, so 1 and then this. And then these were the original superposition amplitudes. So this is 1/4, this is square root of 3/4. It's exactly square root of 3 more, and then we normalize. I'm sure there's a way to do it with inner products. I'm just kind of blanking on it right now, like we did the inner product stuff yesterday. But yeah, that's the partial entanglement. With, so, for example, we're looking at, let's look at this example here, 6.2. So they want to know, if we look at this state, that's 1/2 squared to 2. Three squared to 2/2, 1, 1. If we measure the left qubit, what outcomes can you get? What are the corresponding probabilities, and what did the state collapse do for each outcome? So this will be great to practice what they were doing up here. So if we measure the left qubit, we will get 0 with probability. So take the norm squares of our probabilities, or our amplitudes here. so left cubit will be 0 with probability 3 over 4 times 2, 3 over 8 plus 1 over 8, 4 eighths, so 1/2. And similarly, I mean, they are the same here for the pairs, right? We can see that 1 over square root of 2, 1 square root of 2. So we get 0 and we get 1/2 with probability of 1/2, 1 with 1/2. The states collapse. So for 0, the states collapse to 0, 0, 0, 1 with amplitudes. Again, we can look at the amplitudes here. So this amplitude is our right amplitude, our 1 over 2 square roots of 2 multiplied by square root of 3. So square root of 3 plus, 1. And we need to normalize this. So just as in the previous example, we'll bring in and multiply each of these by 1/2. So now that they're normalized. So we wind up with 1/2. Sorry, I should have left more space here. So 0 with probability 1/2, and it collapses to state 0, and then this superposition for the second cubit. Similarly with state 1, probability of 1/2 that the left cubit will be 1. So and then we collapse to left cubit state 1, and pretty much the same thing here, except the amplitudes are going to be on opposite sides here. So 1/2, 1, 0, and square root of 3 over 2, 1, 1. So is this state a product state, partially entangled state, or maximally entangled state? Well, we could take a look and see if this could be factored. We could take a look and see if, but we know that when we in a non-entangled state, that it does not affect the amplitudes of other states when the cubit is measured. So before, the left cubit had a probability of 1 over 2 square roots of 2 square root of 3 over plus, so pardon me, the norm square of 1 over 2 square roots of 2 and square root of 3 over 2 square roots of 2 of being 1. Right? So the second cubit, before we did any measurements of, let's say the second cubit, the probability of it being in 0 was exactly 1/2. And the probability of the second cubit being 1 was 1/2. Because for the states in the superposition where this is true, we had these amplitudes, right? So second cubit is 0 with square root of 3, 2 square roots of 2. Second cubit is 0 with 1 over 2 square roots of 2. So that gives us 1/2. Similarly, before any measurement, looking at the raw amplitudes and the raw probabilities before any measurements occurred, the second cubit had a 1 over 2 square roots of 2 squared plus square root of 3 over 2 square roots of 2 squared probability of being 1. Now, after we measured, we went from 1/2 to our results here. So we now have we had a 1/2% chance, 1/2 probability of being 0 for the first cubit, and a 1/2% chance, or a 1/4, because we take our squared amplitude here, plus we had, for 1, we had a 1/2 chance of going into this state, and we had a, oh sorry, I should be doing 0 right now, my apologies. We had a 1/2 chance of getting the 0, and then furthermore we had a 3/4 probability there of the second cubit being 0. Similarly, we had a 1/2 chance of the first cubit being 1, and then the second cubit being 0 was 1/2, so 1/4. So after we measure, the probability of being in 0 for the second cubit has gone from 1/2 to 3/8 plus 1/8, or 1/2. We've maintained the amplitude. We've maintained the probability. Similarly, for the second cubit being 1, it's 1/2 times 1/2 plus 1/2 plus 3/4, same thing, right? So measuring the first cubit actually didn't shift the amplitude of the probability of the second cubit being 0 or 1. So I'm going to argue that this state is a product state. It's not entangled. We can check that in the textbook, 6.2. Partially entangled. Oh, I see. 0, probably 1/2 of the state collapses there. Equals 0, 1/2. Oh, I see. Because the all right. Yeah, I see what's going on here. It's altered the probabilities. Okay. So I get it. It is not a product state. I am incorrect. It is partially entangled because measuring the first cubit due to measurement of the first cubit affecting but not determining the second cubit. It wasn't deterministic. So like we were looking at in the Bell states, like this one here, if it's maximally entangled, then measuring any given qubit basically locks in the state for other qubits, for all other qubits. It determines. Let's not say locks in. It determines. Measuring one qubit determines the state for all others. They collapse to a certain state given all other qubits. So here, it does affect the superposition. Oh yeah, it's not 0, 0. Sorry, it's 0 and 1. 0 and 1. So it does affect the superposition from here to here. But it does not say, one of these amplitudes is not 100, right? So it leads to a second superposition. Therefore, it's not maximally entangled. Okay. Let's look at yeah, I mean, as an example of something that's we can tell by looking at this that it's maximally entangled, but we can prove this by saying that the probability of 0 of the first qubit measuring 0 is 1/2, right? And then after we measure the 0, the state collapses to 0, 1. And that infers that there's an amplitude of 1 here, right? So we measure 0. The second qubit has no other state other than 1 to go into. If we measure 1, well, we know that we'll get the first qubit will be 1 with a probability of 0, or with probability of 1/2, sorry. But then we transition to the state 1, 0 with an amplitude of 1. So this is maximal entanglement. Entanglement. The Bell inequalities, honestly, I read through this part of the textbook and I thought it was interesting. I don't think we need to know about this. It's just talking about how is there some type of mechanism that governs measurement outcomes, right? If there's some type of hidden variable that is predetermined that affects, like, because quantum measurement occurs so quickly that it's instantaneous, so there must be, I don't know, this is more physics related. So I don't think necessarily we need to understand the EPR paradox for the exam. Same thing with the CH-SH inequality. Very cool stuff. I read this section, but I retained very little of it, and it's not something that we've had to use on any assignments or seen in any lectures. So it just basically proved that there is some measurement S that, what is S again? The Bell inequality is that S is the less than or greater to 2, which is the S is the quantum, is the sum and subtraction of the various quantum correlations between. Yeah, I read over this. Not important. Unless they really want to test our theoretical chops, I think we could skip that. The no signaling principle is just an extension of that. So it has to do with, I think it kind of paves the way for a little bit of what we look at it with superdense and quantum teleportation. But again, not something that is super important to understand the principles of exactly. Basically, that what's the deal here? So right now, if you want to send a message, you have to physically send the bits via some physical means like radio or fiber optic cable, right, or etc. But if we have quantum bits, well, the answer to the question was, can we use entanglement to communicate faster than light? Because theoretically, classical communication is cannot exceed the speed of light, right? So to communicate faster than light, well, the problem is that in order to, as we'll see with like superdense and some of the quantum communication methods, the problem is that you always need a classical channel. Classical channel to share relevant information like the basis, like in BB84. Whatever, so let's say they have some type of a quantum channel where they're communicating. And even if the bits are entangled, like we see with superdense, they still need to they still need to know the bases that were used for encoding and decoding to make sure that they are getting the right stuff. Like in BB84, they have to have a classical channel to share the basis after encoding and decoding to ensure accuracy and eavesdropping protection. So essentially, you can send qubits faster than the speed of light, theoretically, right? Since it's instantaneous. The entangled qubits, measuring, etc., it's all instantaneous, which is faster than the speed of light. Instantaneous. But there will always be a classical channel. So you will never be able to fully communicate. You can send qubits, but you'll have to rely on a classical channel to transmit the non-quantum information that is relevant for communication. So we'll move through the theories here, etc. So we can move into some stuff about the correlations here. And then we'll look at superdense. Cool. So let's say we have Alice, Bob and Charlie, and they each have their own bits. So let's say Alice and Bob have their own bits, and these are perfectly correlated. So if Alice's bit is 0, Bob's bit will also be 0, and vice versa for 1. And we can also have a third party here that can be perfectly correlated with the two of them. So the idea with perfect correlation here is that regardless of who we have, if we remove Bob, if he's gone, then Alice and Charlie will have the same correlation. Basically, if all parties have perfect classical correlation, then it doesn't matter who we remove. Perfect correlation is maintained. Whoever's left will have perfect correlation with, we could have any combination, etc. As long as our parties are perfectly correlated, then it doesn't matter, right? We could take out half the people, everyone will still, it won't affect the distribution of bit values. So the question then arises, can we do this with entanglement? So we have this example here where Alice and Bob are in this entangled, maximally entangled quantum state, one of our Bell states, right? Which is whatever square root of 2. And then they represent this as the tensor product. 0, 0, plus 1, tensor product with 1. So we need to add Charlie in there. And we'll just call his qubit psi c. So we have to then have a 3-qubit state that looks like this. Tensor product with his qubit. But the issue is that the issue is, are they entangled to the same degree? If we swap in Charlie in here for Bob, right? Let's say this is A and B, A and B. So in their maximally entangled state, how do we know that she is maximally entangled with this one, right? So if we bring this through, let's say we drop Bob and we bring in Charlie. The maximal entanglement is not maintained. In fact, this is not entangled at all because this can be pulled out, right? So we know that if we can factor out a product state, it's not entangled. So this is the very fact that, through the distributive property, we would essentially wind up with, if we tried to put all these into a superposition, right, we would wind up with 1 over square root of 2, 0, 0, Charlie, plus 1, 1, Charlie. With the two previous states, with Alice and Bob's qubits, they can't be factored. But now, we could simply just pull out Charlie's qubit out to this state again. Therefore, neither Alice nor Bob are entangled with Charlie. So entanglement in this way is referred to as monogamous. So 2 qubits that are perfectly entangled. Ugh, okay. Let me get some space here. Are not entangled with a third party. If they're partially entangled, we can do that, but as they state here, that is proving that, and examples of that is beyond the scope of this textbook. So we can, if we have, so for example here, we have 3 qubits that are all perfectly entangled. And let's say that we want to bring in another qubit that is in a let's say a Hadamard superposition, right? 0 and 1. The issue is that due to the fact that this is already maximally entangled, taking the tensor product of another qubit just means that we will always be able to factor this qubit out. We can distribute this through, we can change the amplitudes, etc., right? We could wind up with, this, or 1, 1, 1, right, with some new amplitudes, or, sorry, this is actually maximally, this is a terrible example, because this is actually maximally entangled. We could wind up with a state of 4 qubits in some form, but the issue is that we'll always be able to pull this out. We can distribute it in and we can factor it back out, right? So the monogamy of maximal entanglement applies here. Maximal entanglement there, we can't add another qubit to it to an already maximally entangled state without changing, we can't add another qubit to a maximally entangled state and have it be, still be maximally entangled due to that factoring. Okay, that sets us up for superdense coding, which I believe we did, that was in our lab. Let me check. I just want to see if that was part of our assignments, grade scope. one code. What was the question 4? I don't remember which one the super dense was. Quantum adder. Maybe this. Maybe. Okay, so we had BB84 on the first lab, and we had. I don't think we had super dense coding on the first lab. I think it was on the second lab. Okay, cool. I just wanted to see if that was gonna lay the foundation for anything. Okay, so super dense coding. Is a way that we can send 2 bits of information, of classical bits, pardon me, with 1 quantum bit, with 1 qubit. And the way that that works out is that we have a quantum solution, right? So if I want to send 0, 0, classically, I would need to send 0, 0. And any bit that I send needs to, any bit of a message that I want to send has to have a corresponding bit in the message that conveys that information. However, with the quantum, in the quantum realm, the quantumania, we can create entangled states, right? So these entangled states can create entangled superpositions, which have very specific qubit states. And then basically we agree on, see if I can remember how this was played out in the lab. So basically for each, I'm trying to remember exactly how we implemented this. Okay, gotcha. So the idea is we use the Bell basis. Now, if we create an entangled pair of qubits such that 1 qubit goes to Alice and 1 qubit goes to Bob. Oh, well, I don't need to write qubit there. We create an EPR pair, Einstein something Rosenberg. Anyway, we take 2 qubits and we create an EPR pair, which just is that we entangle them into a Bell state. So one of our 4 maximally entangled states. And then we give one of those qubits to Alice and one of those qubits to Bob. So those 2 qubits are entangled, so whatever Alice does to hers will affect the qubit that Bob has. So if she wants to send 0, 0, sorry, let me just walk through exactly what they have here. So we create some entangled Bell state. Let's say it's this one. Left qubit, let's say the left qubit goes to Alice, the right qubit goes to Bob. So if Alice wants to send 0, 0, she does nothing. So then she sends her qubit to him, and he'll measure in the Bell basis and decode 0, 0. If she wants to send 0, 1, she will apply the X gate to her qubit. Now, applying the X gate to her qubit is going to have the same, it's because they're maximally entangled, will affect his qubit as well. So we'll go from our original state into 1, 0 plus 0, 1. Bob's qubit will also be changed, also be affected because they're maximally entangled. If she wants to send 1, 0, she would apply the Z gate. Apply the Z gate. As we know, the Z gate leaves 0 as 0, maps 0 to state 0, and negates the amplitude of state 1. So she would wind up with this would alter the maximally entangled state to 0, 0 minus 1, 1. Similarly, if she wants to send 1, 1, she would apply both an X and a Z to her qubit. So applying the X and the Z, to this original state that she's in, gives us, well, we know that X flips the amplitudes, so we wind up with 1 over square root of 2 0, 0 transfers to plus 1, 1, or pardon me, ugh. So she applies the X to hers, and we wind up with 1, 0 plus 0, 1. And then the Z gate applied to that is going to negate the amplitude of the 0. And I got a little turned around here, my apologies. Oh, right. Two, 0, 0. Applying the X gate leads us to, does it just to 1, 0, and 0, 1. And then we wind up with she applies the Z gate, which negates the amplitude for the qubit state where she has 1, and we wind up with 1 over square root of 2 0, 1 minus, because it negates the amplitude here, 1, 0. So then, so after these various transformations are done based on what she wants to send, she sends her qubits to Bob. He sends her qubit to Bob, and they're in one of these 4 states. They're in the Bell basis. So using this Bell basis, oh Lord, plus candelabra plus minus. We can use this as a basis for measurement, and the Bell measurement occurs, measuring in this basis, and it will give him whatever information that she was trying to send. So similarly, they have a way that demonstrates it with just gates. So we can walk through that. So let's say, you know, she sends zero, she wants to send him 0, 0. So she leaves the original, her qubit untouched. So we still have this original superposition, this maximally entangled superposition. So we wind up with our original superposition is 1/2 0, 0, or 1 square root of 2, pardon me, plus state 1, 1. We apply, so first they say to apply a C naught. So we apply a C naught to this state, this superposition here. C naught operates via the matrix form is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It flips when we have 1 here, right? 1, 0, 1, 1. It's going to flip those amplitudes. So we wind up with a position of plus and 0. And then when we apply the Hadamard and identity gate, right? So we want to apply the Hadamard to the, as we discussed yesterday, this essentially, taking the tensor product of two gates allows us to have action for each gate that is specific to a single qubit. So the H will be applied to our first qubit, and the I will be applied to our second qubit. So the second qubit will be maintained. So when we know that when we apply a Hadamard to a plus, it just gives us 0, because plus is just a 180-degree rotation from 0 caused by the Hadamard gate originally. So applying a Hadamard back just rotates us another 180 degrees back around to 0. So we wind up with 0, 0 after we apply this gate here. So computationally, and this is what bugged me, right? A lot of stuff in the class so far, they like to fudge the numbers a little bit to make it seem like it's more powerful than it actually is. But so it still requires 2 qubits. So it's really still requires 2 qubits. We have to generate a pair of maximally entangled qubits. It's just that Alice only has to send 1 qubit to Bob when she wants to send a message. However, I don't know. Again, 2 qubits are created, and then one of them has to be sent to Bob anyway, and then she has to send. It's I don't know, it might be more efficient. It might be quicker. I don't know, but the quantum supremacy for me is questionable on this one. So yeah, so example here in 6.13, they want us to verify that the Bell states are orthonormal to each other. We know that for states to be basis for measurement, they have to be orthonormal, and thus have inner products of 0. So if we went through and we broke down each of these, right, if we took this one with minus, we took the inner product, or we took that one with candelabra plus, we would find that every combination between these two of inner products would all be 0. And that's, I won't work through that unless you guys absolutely want to see an example, because we've looked at something similar before. But in the answers, it does show let's see. Yes, it does show the just that each of the inner products is equal to 0, unless they are it's the inner product of a state with itself, in which case we're 1. So so 6.14. So she wants to send one of 16 possible states to Bob. So we have a bit string, bit string of length n equals 16. So let's say, for example, a state in this string could be 15 zeros and a 1. Or it could be 14 zeros, a 1, and then a 0, right? We could denote 60 different positions by just having a 1 bit in a different position of each bit string and having all the others be zeros. So she would need 16 classical bits to send one of a possible 16 states. How many qubits would Alice need to send if they share entanglement? Well, we know that 1 qubit can send, theoretically, can encapsulate 2 classical bits. So she would only need 8 qubits. 8 qubits to send the equivalent of 16 classical bits, completely glazing over the fact that 16 qubits have to exist anyway for this communication protocol to work. So yes, including, so see how many qubits total would it take? It's 16 qubits, so 18 for Alice, or 8 for Alice and 8 for Bob. So the circuit diagram that they have here is that the maximally entangled state plus, oh Lord, is created with having 2 qubits, both starting in 0, applying a Hadamard gate to the first qubit, and then using that as a control for a C0 up here with the second qubit. The Hadamard gate creates the superposition, and then the C0 creates the entanglement. All right. So, is everyone good on that, or do I need to break anything down? Okay. We'll move on to quantum teleportation. Yes. Yes, because each qubit, 1 qubit encapsulates 2 classical bits. If it's 2. Is that what I said? Oh, my apologies. 6.14. I thought they were asking for the total number of qubits. How many classical bits would she need to send to him? 6.14. 2. Oh, I see. Yeah. What is it for? How many classical bits would she need to send to him? Oh, wait a second. No, it's not. Okay, I got it. I was assuming that when they said 16 possible states, they meant that we needed a bit length, a string of bit length 16. But because each bit can represent 0 or 1, we only need, to represent 16 states, we only need 2 to the 4th. Yeah. So we could have, yeah, I was thinking but it's much more efficient to have the states like that, right? We can represent 16 different ones like that. So, yes. So n is 4, and so to send 4 bits, she would only need to send 2 qubits, and it would take 4 total qubits, 2 for each of them. Thank you for catching that. I would have completely just moved on from that. I didn't get that they were asking for 2 to the 4th, 2 to n instead of. Okay. Any last thing on superdense coding, or are we good to move back onto teleportation? Awesome. Okay, so teleportation. So let's say that we want to send an unknown state psi from Alice to Bob. She doesn't know it, obviously, because of the no cloning theory, no cloning theorem. She can't replicate the information by measurement because it will change, it will collapse the superposition and destroy the original superposition information that was there. So how did we get this quantum information, this unknown state, to Bob? So basically, if we had a ton of different qubits, each one is exactly in this psi, then she could do a bunch of different measurements in possibly a bunch of different bases. And over time, with enough examples, she could kind of figure out what the state, the superposition of psi is, with enough measurements, with enough copies, or not copies, but with enough qubits in state psi, she could measure in many different bases and kind of interpret over examples the superposition. However, for the purposes of quantum teleportation, she only has one of these, and we can't make any copies because unknown quantum states can't be cloned. So even if she did somehow manage to know what psi is, the amplitudes could be complex, and they could be rational or irrational. Complex, rational, or irrational. And the number of bits that would be necessary to express, let's say, an irrational number like pi, for example, is infinite. So there's no way for her to effectively share rational complex numbers accurately. without having unlimited resources. So she doesn't have unlimited size that she can do some type of measurement test with and figure out the superposition over time. And even if she did know it, she doesn't have the resources to transmit the complex amplitudes due to the size of the decimals that might be in those rational and irrational results. So we can similar to superdense coding, we can use entanglement. So let's say that we have, again, we'll use this original one of the Bell states that we were talking about, which is equal to 1 over square root of 2, 0, 0, plus 1. Okay. And we can take this, we can take the tensor product of our psi with our entangled state, or rather, sorry, it should be the other way around. Wait, which one is this? Psi. Tensor product with our entangled qubits, creating what we have down here, which is 1 over square root of 2 alpha. Alpha is the amplitude of our psi state that we don't know. And we wind up with, oh, switch lines all of a sudden. All right. 0, 0 plus 1, 1, and plus beta 1, 0 plus 1, 1, 1. So the left two qubits are hers. The right qubit is his. What was this? Is it a plus? Yeah, it's a plus. So these are Alice's. So she will apply a Hadamard gate to the left qubit, and inferring that an identity gate will be applied to the other. So we know we're going to have a tensor product of H, I, and I. We just want to affect the first qubit. The second and third qubits will be unaffected. And after she applies the Hadamard to the first qubit, we wind up with this final state, which is long. I'm going to need to get some extra space here. Okay. So we wind up with 1 over 2, 0, 0, 0, alpha 0. You know what? I'm going to work through this. I think the best way, instead of just regurgitating the result from the end, I will actually just work through what applying the Hadamard gate to the left qubit does. So we're in this state currently. Once we take our tensor product, and then we apply. Oh, and I skipped over the C naught. Oh, fantastic. So I got the cart ahead of the horse anyway. All right, so we take so step 1, we have the tensor product of the entangled state that they share. State that Alice and Bob share. And just like in superdense coding, the benefit is that whatever she does to her qubits will also affect his qubits. So first she's going to do a C naught to her first 2 qubits. To her C naught to her 2 qubits, which are the 2 left qubits in each state. To her 2 qubits. So what we wind up with is, so we have C naught, tensored C naught. I won't do the matrix form of that. I'll just distribute it through and work it that way. So we have 1 over square root of 2 alpha C naught 0, C naught 0 and 0 plus C naught of 0, C naught of 1 and 1 plus beta of C naught of 1, C naught of 0, say 0 plus C naught of, yeah, this is the equivalent of doing this, just for clarity's sake, right? Identity gate's just getting applied here, so it's the same thing. It maintains. So C naught of 1, C naught 1, 1. Okay. So once we evaluate that, we wind up with 1 over square root of 2 alpha, state 1. That 0 turns into a 1. Wait, what happened here? Oh, it's a C naught. Oh, Lord. It's not an X gate. Sorry, guys. I'm flagging today. Why is there a ruler on the screen? Okay. It's a controlled knot. I'm tripping. So, it's a controlled knot. So it's applied to the first 2 qubits. It's not an X gate. This is a multiple qubit gate. So the C naught is applied to 0, 0. We'll just draw the little tensor thing in there to understand what's going on there. C naught of 0, 1. C naught of 1, 1. And C naught of 1, 0. Leaving us with 0, 0, 0 plus there we go, 0, 0, 0 plus 0, 1, 1, so that's unchanged, plus beta 1, 1, 0 plus 1, 0, 1. Okay. Now step 3, she'll apply a Hadamard gate to the leftmost qubit. Hadamard to leftmost qubit. There's 2 U's there, we'll let it slide. Okay, so we're in this state. We're going to apply Hadamards to the leftmost, so we'll wind up with one over square root of 2 Hadamard of 1. Zero plus Hadamard of 0, 1, 1 plus beta Hadamard of 1, 1, 0 plus Hadamard of 1, 0, 1. So the Hadamard will evaluate. It'll change zeros into an equal superposition of 0 and 1. 0, 1, we'll just work it out here. Alpha, 1 square root of 2, 0 minus state 1, 0, 0 plus 1 over square root of 2, 1 over square root of 2, 0 plus state 1, 1, 1 plus beta 1 over square root of 2, 0 minus 1, 1, 1, or pardon me, 1, 0. And 1 over square root of 2, state 0 minus state 1, 0, 1. And then that all simplifies down to the form that we see at the bottom. We would pull out our 1 over square root of 2, and that becomes 1/2. We are distributing through, so a few things are going to cancel out, right? So, for example, we wind up with, so let's leave alpha here. Now we have our 1 square root of 2 out. Each of these is going to distribute through. We'll have 0, 0, 0 minus 1, 0, 0. Plus 0, 1, 1 plus 1, 1, 1 plus beta of 0, 1, 0 plus, or pardon me, minus 1, 1, 0 plus 0, 0, 1, 0, 1, and 1, 0, 1. So I see the big difference here is that they just left them in pluses and minuses, and they didn't go into this longhand form. And that complicates it, because then how do I... Oh, I see. Okay. We can group factorable terms together. Yeah. It'll just take a little bit longer. We'll get to the same place. So we can distribute our... we can group like terms. So for example, we have... we can group our, for example, this state and this state together because they both have the 2 qubits are 0, 0, and we can pull out that 0, 0, and we have alpha of 0 minus, plus beta of 1. Similarly, we can group these two together. Let's switch colors here. We can group these two together. And we could pull out the 1, 0. And we wind up with alpha state 0 plus, minus beta of 1. Similarly, we can group these together. They both have the 0, 1 here. So we can bring that over and say 0, 1, 0, 1, beta of state 0 plus alpha of 1. Of 1. Lord, the brain is not wanting to cooperate tonight. And finally, we can excuse me. We can pull out the 1, 1 terms. Plus alpha of 1 minus beta of 0. Now we're in this funky position here. She can now run a measurement in which basis? What are they going to specify here? Oh, I see. Oh, I get it. Okay, so basically what's happened here is that each of these unique superpositions within here, right? Each of these can be their own thing, right? So when she measures her 2 qubits, after she creates this, then she'll get one of the 4 possible states. For example, so if she gets 0, 0, then she knows this is the result. So for example, if she measures and gets 0, 0, then he now knows that this alpha 0 plus beta 1 is the original where is it? All the way up here, right? We said we had this arbitrary psi, alpha state 0 plus beta state 1, that we're trying to send. We don't know it, but through the application of the tensor product and then applying these gates, we've now kind of like encoded into this state what the original state was. Bob just has to have some extra steps. So if she sends 0, 0 to him, then he knows that his 3rd qubit, because this is his, right? Remember, the first 2 were hers, the last qubit was his. He now knows that the qubit that he has is in the superposition psi that we were trying to find out. If she measures 0, 1, well, he knows that we are currently in A0 minus beta state 1 Then he applies an X gate to his qubit. Did I write this correctly? They had some things that were, so 1, 0, yeah. She measures 0, 1. Oh no, they had, oh no, they did, sorry. I miswrote it here. Beta 0, alpha 1, plus 1, sorry. So basically he knows that if she sends him 0, 1, all he needs to do to get the superposition psi is to apply the X gate to his qubit. It'll switch the amplitudes, and he'll wind up with this state, which is psi. Similarly, if she sends 1, 0, well, he knows that it's in form alpha state 0 minus beta state 1. Well, he needs the original psi. To get there, we apply the Z gate, which doesn't touch the amplitude for the 0 state, but negates the amplitude for the 1 state. So he winds up with alpha state 0 plus beta state 1, which is psi. Finally, if he wants 1 and 1, if she sends him 1 and 1, pardon me, then he applies an X gate and a Z gate to this superposition. So the X gate swaps the amplitudes. So the X gate will make this into alpha 0, alpha or minus alpha 0, no, I apologize, beta of 1 minus alpha of 0, and then he will apply a Z gate wait a second, did I miswrite this again? I did. I apologize. This is actually the first time since we went over this in class that I've actually worked through this longhand again. A little... Okay, let me erase this and rewrite this. I think having it in the form that they have it there allows it to make more sense. Yeah. So, yeah, that's... so... minus beta 0 plus alpha 1. So when they switch the amplitudes, we wind up with alpha 0 minus beta. The minus transfers over as well. I don't know why I thought it would be minus alpha 0. So alpha 0 minus beta 1. Then we apply the Z gate, which maintains the amplitude for the 0 state and negates the amplitude for the 1 state, and we wind up with the original state psi. Woo! Okay, wow. Thanks for sticking with me through that. I guess the perks of review, right? You learn what you actually remember. So, yeah, so basically we can take any arbitrary state psi, we can manipulate it in tandem with any of our maximally entangled Bell states, and we can essentially wind up with a system where whatever she measures gives him information about what he needs to apply to his qubit. So, you know, this the quantum teleportation has a quantum channel, which qubits are sent over. But there's also a classical channel where she tells him the results of her bits, of her bit measurements. So she sends 2 bits of classical information. And that allows Bob to look at, apply the gates to his qubit, and get this original superposition psi that we didn't know. All right, if everyone's cool with that, we will look at the circuit implementation. Yes. Right. So we already have, so remember what we were talking about how with monogamy, how when we have 2, if any qubits are perfect or maximally entangled, then when we pull out something, when we try to add another qubit in to that superposition, it alters the maximal entanglement of that. It creates partial entanglement because we will be able to always factor out and pull out psi. So this is just the way. So when we take the tensor product, we are just not adding, we're multiplying, we're distributing in psi into the original maximally entangled superposition. So that's just a way to get it in there into like one big superposition. And then we can use our gate sequences here to manipulate. And essentially, if you'll see, what happens is that we wind up pretty much factoring out a product state near the end. The effect of doing the tensor product and then applying all these gates basically winds up with this kind of key dictionary system where we're in this big combined superposition, but each of the superpositions that match up with each of the 2 qubit sequences that are Alice's gives us information about what the 3rd qubit superposition is. So the tensor product is necessary to start that process, to get the psi qubit, the unknown qubit, into the entanglement. And then through this, we can factor it out into its own product state again, but this time with the relevant information necessary. Yeah, because right. So when we have, I mean, also it's a tensor product because that's what like if we have just 0, 0, and 0, it's the tensor product of those 3, right? So if we want to have Alice's qubits, Bob's qubits, and this unknown state psi, we'll need to take the superposition that already exists and do a tensor product with that. But yeah, it's just about getting in, and we have a maximal entanglement, and we create a partial entanglement that gives us those product states. And each of these are different forms of these. Each of these are like different transformed psis. These are just psis where, through those applications of the gates, the C-naughts and the Hadamards, things have happened to the psi that are reflected in each of these. And then Bob just knows, once he receives over the classical channel 0, 0 or 1, 0 or 0, 1, what he needs to do. Yeah, pretty much. So the circuit diagram here um, leaves out the part that we looked at earlier where you actually, so before we get to the circuit here, you have to first create the entangled pair of qubits. And that was, as we saw, just achieved with a Hadamard and a controlled knot between two qubits. The Hadamard creates the superposition for qubit 0 and then entangles it with qubit 1 using the C knot. And then here we take the official circuit for quantum teleportation is we have the entangled pairs of qubits in, let's say, state whatever this thing is, and we have our unknown qubit psi, which has this unknown superposition. We apply a C knot here, and then an H. So the C knot is applied to the first qubits of Alice's 2 qubits. That's what this represents. Sorry, this is what Alice's, this C knot is the C knot of the first two qubits in our new superposition. Then we apply an H to psi. There'll be a measurement down here. Another measurement. And I don't remember what these like hollow things here represent. I think they're just like conditionals. Depending on various conditions, we would apply these. Like that's why they're not so depending on various conditions, we would apply these X and Z gates, right? Depending on what she sends him over the classical channel. And then he gets the psi here. So we have our entangled pair. This is Bob's qubit. These are Alice's qubits. We create the superposition with Q0, the gate up here. And then we apply the C knot with the first 2 qubits of Alice's sequence. Also, yeah, sorry, that's another thing I should have clarified about up here, is that'll help answer. So the reason why when we do the tensor product, instead of doing this, instead of doing this, we do it this way, is that so that Alice's first 2 qubits are on the left. So basically we have her, so we have A and B, right? Which is, let's just, the 2 qubits in this superposition, qubits A and B, that make up this. And then when we bring in the tensor product, what we wind up with is a superposition of the tensor products of psi A and B. So the first 2 represent Alice's qubits, and we can interact with these 2 qubits to pass the information along to his qubit down here. So yeah, instead of what we would have here would be A, B. If we did it this way, we would have A, B, and psi. So then she would have to be operating on the first and third qubits. His would be the middle. I think it's just for ease of notation, instead of having to make things a lot more complicated by having the middle qubit be Bob's. We just do the psi here, and so that way the first 2 we can just work with those in nice, in this diagram, for example, we know looking at these 2 that they're hers and this is his, instead of having to have something more complicated going on. So I don't remember deferred measurement, honestly, from page 194. Let's navigate back and look at that. 194. Oh yeah, it was during the intermediate measurements that are used to move after the operations, and the controls can be replaced by quantum controls. Okay. Back to 2. Let's see. Where we were. Yeah, so that's quantum teleportation. By using an entangled set with, we can manipulate it with an unknown. We can manipulate an entangled pair of qubits with an unknown state psi to create information that allows a receiver to get the unknown state psi without any type of measurement or any type of or any cloning. Obviously, we can't do any cloning, but yeah. So there is that. Do you guys want to do a practice problem, or should we move on from teleportation? Okay. Okay, perfect. Yeah. Awesome. Yeah, I'd like to. So, quantum key distribution. Can't remember if we had to do this in. No. So, yeah, this is just an overview of the first part. Here is an example for how you create, a key, and essentially just a bit string of ones and zeros that we can use to encrypt plain text bit strings into into ciphertext, and then transmit the ciphertext. And obviously they share the key, so whoever receives it can decode it. RSA is a thing. It's been like 3 years since I've looked at the RSA protocol for cybersec, so I'm not really going to go too in depth about that. We can just move on to the quantum implementation. All right, so BB84. We talked about this briefly when we were looking over the knowledge check, I think maybe a couple days ago, but really quick, just a really, since this will be like the second or third time that we've discussed this, it's a, oh gosh, let me make this larger. All right, cool. It's a form of quantum key distribution. Basically, and it does not use entanglement like the superdense or teleportation that we looked at. We have a quantum channel. We have a classical channel. We have go to our good friends Alice and Bob again. We have some eavesdropper who can potentially listen in on the conversation. We'll call her Eve, right? And step one, Alice randomly chooses. So we have a bit sequence. And she randomly selects a basis, right? And she either chooses the computational or Z basis, or the X basis, which is plus minus, or Z basis, which is 0, 1. So she either sends him So if the bit is 0, she will send him, if you use the z basis, she'll send him 0. If it's the x basis, she'll send him plus. And transversely for 1, if it's the z basis is selected, again, this is a random process. When we built it in the lab, I believe it just randomly selected that. So if the z basis is randomly selected, it'll send 1, state 1. Or if the x basis is chosen, it'll send state minus. Afterward, she'll send this to him. He will also randomly choose, so 2, send to Bob. 3, he will randomly choose a basis, either the z or x. Choose z or x, and he will then get some measurement, right? And he'll measure, and he'll get some outcomes. So zeros or ones with some arbitrariness, right? Because we're randomly choosing. He'll get 0 or 1 basically. And then once he has decoded, Alice over the classical channel will send him the bases that she used for the bits. If the bases were the same, the base that she used to encode and the base that he used to decode. So if the bases are the same, they should have the same information. If not, if they're the same, so if not, so if same but different information, eavesdropping, right? Someone has intercepted that qubit on the way, and they also had to make a decision about what basis to measure in, because they were trying to get the information out of the qubit, and there's no way to get the information from the qubit unless you measure it. So they had to randomly choose a basis to measure in. They measured in the wrong base, and the state collapsed to some value in the wrong basis. And when he measured, despite the fact having the same using the same basis for decoding that Alice used for encoding, he will get the wrong result. So they discard bits that are different, and they retransmit until everything is good, right? And they iteratively do this and retransmit. And we looked at the knowledge check yesterday with the probabilities, right? The eavesdropper has a 75% chance of getting the correct information with each transmission. 50% probability of choosing the right information, and then a further 50% chance of the measurement of the state that it actually collapses to being accurate, right? So Alice could want to send a 0 in Hadamard, and it could collapse to state 1, right, when you're measured, because they have equal probabilities. So that's why they discard any bits that are different, not just because of eavesdropping, but also due to the probabilities of the superpositions playing into it. They could have the same basis, but they could also just be collapsing to different states because of the superposition. So Alice could encode in the z basis, he could decode it in the z basis, but get the opposite result just because of the 1/2 chance. And that's BB84, right? So yeah, that is that is that for BB-84. I think we're good to move on from that. Is everyone okay with BB-84? Awesome. Okay, so the big kahuna, right? Literally like the next 150 pages of the textbook. Almost like a third of the textbook is this chapter. It is a big boy. So what is it? 605. I really wanted to try to push through as much of this as possible. Yeah, tell you what, let's push through this for another hour, and then take a look at the lab after this, if everyone's okay with that. I just want to try to get through as much of this today, so that we can spend like tomorrow and even parts of Saturday if we need, to go over the algorithms. So quantum algos, the what we're the whole goal of quantum research to get us to quantum supremacy, where we have things that can theoretically do things faster than classical, right? So how do we distinguish if a, let me start a new whiteboard, sorry. So how do we distinguish between performance, right? Between quantum versus classical. Well, in classical computing, and we'll just call that CC for shorthand here, we have circuit complexity, right? We have different gates with different numbers of gates for different tasks. So the issue is, in quantum, circuit complexity is way more way more difficult to determine, because we have different universal sets. So there are several different universal sets in of quantum gates. That can build circuits. They build any gate for any circuit. So any circuit. So how are we supposed to know? For example, right, we were talking about yesterday, right? C naught, H, and T are a universal set. H and any unitary 2-qubit gate are a universal set. We have any number of different universal sets we can have. So when we look at, is a quantum circuit superior to a classical circuit in terms of how many gates there are, well, that can differ, right? Depending on what we're building these gates out of. And for example, a Toffoli gate can be decomposed into the sequence that they show here. Well, if we use one Toffoli gate, what is the circuit complexity of that? Are we going to say that's one gate? Or is it, whoa, hang on. If we're going to measure circuit complexity, you have to factor in the number of gates for each gate, the number of gates that each gate can be decomposed into in its simplest form, right? So unlike classical gates, where we have like circuit complexity is very easy to look at, because of the demands of quantum gates and just the wealth of ability that we have to build them from various smaller gates, circuit complexity is a lot harder to figure out. So instead, we have query complexity. Right? If we build a circuit how many times do we need to call /query, right? think about it like a circuit is a function. So how many times do we need to call / query the circuit when solving a problem, when solving a given problem? And again, I'm just going to preface this by saying this is another one of those things where they start fudging the numbers a little bit to make quantum look better. Frankly, it's a little sus. But so query complexity is made more opaque, or not made opaque. How's the way that I would put it? So in quantum, we have the oracles, which is a black box function. That it's, again, we don't know what's in there, even though, well, we do know what's in there because we literally built them in labs. But it's an abstract idea, right? We theoretically, we have some oracle, call this super big O, right? We have some oracle circuit that inputs are passed into, and we get outputs that solve a problem, right? And the thing is that we can pass in to an oracle less than we do a classical circuit. So, for example, we were looking at, so they talk about like a search. And whereas with classical, well, actually, I'm not going to get into search because that's actually an example that they talk about later, that go into detail about with some of the oracles. So we can see here it's literally just drawn on the circuit diagram as this thing, right? We don't really, like, what's going on in there? We have no idea. It's like the nightclub you can't get into. And it's, this circuit has, because we need to understand what's going on in terms of when the inputs go in, we need to be able to map them to an output. It needs to be reversible, so we have some type of ancillary qubit that comes in that gives us the XOR of the oracle output, and some, let's call this Y and X. Well, actually X kind of comes up here and then goes in, and then we have to have X on the output as well. But yeah, the oracle circuit is reversible, so we can draw the entire thing as a U gate, right? It's unitary, so we can denote that with just its own. We could take the entire thing and turn it into a gate. So basically the U of F in terms of ket notation takes in state X and state Y, and outputs state X and the XOR of state Y and the output of function F of X into there. So, excuse me. So, for example, if X is 0 and Y is 0, well, Y is initialized as 0, as most qubits are in quantum systems. Then we pass it through our oracle thingy, our entire circuit containing the oracle and the XOR to make it reversible. And we wind up with O and the XOR of O and FO, which is just, again, the XOR is now dependent on what FO is, so we wind up with state O, or pardon me, state 0 and state f of 0. Similarly, if x is 1, we pass it through our complete circuit, and we wind up with 1 and f of 1. X is the input, Y is the target or answer. I don't know if that's important, but we'll write that here. Answer or target. X is the input qubit. So let's look at really quick, just to drive this home. Let's look at 7.1. So we have a classical oracle f of x equals not x, where x is a bit and x is the not of x. So they want us to construct a truth table for state x, state y, f, state x, y, XORed with f of x, where f of x is equal to not x. So what's the truth table? Let's draw it out. X, y, y, XOR f of x. So x is 0, y is 0. So we have 0 XORed with f of x, which is not x. So we have y, or so 0 XORed with 1, which is 1. We have 0 and 1, and we have 1 XORed with f of x, which is not x of 0. So we have 1 XORed with 1, which is 0. Pass through here. Similarly, we have 0 XORed with not x, which is 0. So y XORed with 0, or pardon me, 0 XORed with 0, which is 0. And we have 1 and 1. Y is 1, 1 XORed with not 1, which is 0. So 1 XORed with, pardon me, is 1. So the question is this operation reversible? Yes, because we maintain we can map each output back to its own distinctive input, right? The outputs are not, there's no duplicate outputs for different states, different input states. So this is reversible. Reversible. And C, what is the quantum oracle as a 4x4 matrix? So the quantum oracle applies a C naught to X. So it's an X gate. So we have it's an X gate to input X. And it does not operate on Y. So it inputs the X gate to input X and an identity to input, or pardon me, what do they call it? The answer qubit W. Because W has to come out of the oracle in its original form to be used in the XOR to make the circuit reversible. So we know we have X tensor product I to make it so that this operates on the first and this operates on the second. So the XOR is 0, 1, 1, 0 in matrix form, and identity is 1, 0, 0, 1. We'll take the Kronecker product to get our tensor, our final matrix. So we have to take each element of this matrix and multiply it by the entire identity matrix. So 0 times the identity matrix is 0, 0, and 0. 1 just replicates the identity matrix here. Similarly, we replicate the identity matrix down in the bottom left, and the right will just be 4 zeros here. So this is our quantum oracle in matrix form. Now, is this oracle unitary? Oh, we can find out, right? So we can find out via taking the conjugate transpose. So this is our oracle. This is our oracle conjugate transpose. The dagger thingy here. The little sword. Okay. So 0, 0, 1, 0, 0, 0, 0, 1. There are no complex numbers in here, so we don't need to do any of the conjugation, but we do need to take the transpose of this. Zero, 0, 1, 0, 0. Right? So we take the transpose of that. And what we want to see is the identity matrix, right? So let me for brevity's sake, let's just do this on Desmos. So matrix A is a 4x4. Can you guys see this? Should I zoom in? I'll just zoom in a little bit. So matrix, let's just call this matrix A for our oracle, which is 0, 0, 1, 0, 1, 1. And we'll say B, which is also a 4x4. Not 5, which is and 1. And then we can prove that matrix A times matrix B is equal to the identity matrix here. So the oracle multiplied by its conjugate transpose is equal to the identity matrix. Therefore, it is unitary. And all valid quantum gates must be unitary. So this is a valid the oracle is a valid quantum gate because of its unitary nature. All right. Yeah. Oh, okay. So it's yeah. So basically, the oracle f of x. So in our circuit, it's going to our oracle will output the oracle will give us where's the I'll just go up to the picture here. Sorry. The oracle will give us f of x, and the oracle gives us f of x, which is not x. And also y has to pass through the oracle has to pass through untouched. So you see, like coming into u of f. So they take this entire thing and they put it together as a unitary gate u of f. So y has to emerge from this gate on the other side untouched because we need to use it in the XOR um, in the XOR calculation. So the oracle itself within U needs to take in X, take in Y, perform a not on X because it outputs the not of X, but leave Y untouched. So to do that, to create a quantum gate that operates on a particular qubit, we can do the tensor product of the do a sequence with tensor products, and so this is the tensor product of X and the identity matrix, where this is in the first position, this is in the second position, so it will only work on X, and it will leave Y untouched when it's passed through this matrix, when it does when it's multiplied with this oracle matrix form. Yeah. Yep. Yep. It's the tensor product, the Kronecker, whatever we want to call it. Yeah. Yeah. So we combine the gates together into one. Yep. Okay. So the phase oracles. Um, this is pretty vital for some of the algos that come up. So I'll dive into this. So oh, because of Little Indian format. Okay, I gotcha. So yeah, my apologies, guys. This is this is in this was assuming that we were in this is assuming that we were using Big Indian, right? So that this would be our first qubit and this would be our second qubit. But if Y is our first qubit and this is our second, then we're in. And Qiskit also uses Little Indian, so that's it's important to know. So we would do I tensor product X, so that I would get applied to or rather, no, I'm sorry. It's still, I'm pretty sure. Oh, right, yeah. I think they were just asking for the quantum oracle itself, not the entire circuit. That's what I took this question to be. So they're not asking to combine this with the XOR part. I think they just want the XOR that gives us f of x equals not x. If that makes any sense. Let me look at the answer because I could be. Let me just get the real facts here in terms of what. So okay, yeah, I see. Okay, the outputs are unique. Yeah, let me. Yeah, I think you're correct. It is, which gives us 1 0. Yes, so they're using Little Indian format then. So it would be like that. In the official state, if we were writing this as an official state, it would be XY. And then so we would wind up with 0 1 1 0 0 0 0 0 0 0 0 1 1 0. Yeah. Okay. Thank you for pointing that out. I feel like if they're gonna use a notation on the exam, they'll make that clear. I mean, that could be. You know what? I'll put an edstem, or I'll ask on the discussion board whether or not we're going to use big or little on the exam, because that'll be good to clarify that. To Quizzkit is always little, and we use that on the homeworks, so I assume that'll be what we're using. Um, but yeah, that's a good question to ask before. I mean, I assume that the practice midterm will show some examples. I still have not, by the way, I still have not heard back yet from Lakshmi. I actually DM'd her directly to see if we could do that, if they were going to do extra points for the thing, for the practice, or if not, if we can do it all together as a team. I haven't heard back yet on that. So, phase oracle. So, there's no way to query the quantum. So, if we use the oracle from before, there's no way to query that that causes, oh Lord, causes y to be unchanged while applying a phase to x. Oh, sorry. They're using the standard way. Sorry, using the way we just described. There's no way to cause y to be unchanged while also applying a phase change to x. However, we can do it by turning y into state minus, and then x state 0. We do that. So we've got x, which turns, so we start off with y is equal to 0. We use this I tensor product x to apply an x gate to the y, turning it to 1. And then we apply the tensor product of identity and Hadamard to target the y qubit, and we get x minus. So when we query the oracle, we wind up with a state that gives us an unchanged y, but x has what they call a phase kickback. So we have prepared our two qubits, our input qubit and our answer qubit, to be in form x and state x and state minus. Now we will write this out to see what's going on inside. So that's 0, state 0 minus state 1, amplitude 1 over square root of 2. We'll distribute the x through, and we get 1 over square root of 2 x 0 minus x 1. Now when we apply the U-gate, the classic U-gate to this, right, that we were talking about before, where the output is y or x and y XORed with f of x. This is just an arbitrary, just an arbitrary U-gate, arbitrary oracle, not the one we were talking about earlier. Just this arbitrary oracle outputs x and y XORed with f of x. So we apply our gate, our oracle circuit that we created, our unified one, and we wind up with 1 over square root of 2 of state x y went in as 0. So now we have 0 XORed with f of x. Yes, x. And we wind up with 1 XORed with f of x. So there's two scenarios that can occur here based on what the value of x is. So we can either wind up with f of x equal to 0, or we can wind up with f of x equal to 1, depending on whatever the x value is, right? So, and whatever the oracle is assessing in regards to x. So if f of x is 0, then what we wind up with is 1 over square root of 2 state x, 0 XORed with 0, minus state x, 1 XORed with 0, which gives us 1 over square root of 2 x, and 0 XORed with 0 is simply 0, minus 1 XORed with 0 is 1, so state x and state 1. If f of x is 1, however, then this would equate to 1 over square root of 2 square root of x, 0 XORed with 1, which is 1, minus x XORed with 1 and XOR 1 of 1 with 1, which is 0. So state x, state 0. So, well, how do these differ, right? So they look very similar. We can rewrite them to emphasize that more, right? So 1 over square root of 2, we can pull out the, I say x 0 minus x of 1. We can pull 1 over square root of 2. We can rewrite this minus x, state x of 0, and it's 0 plus plus x and 1. And we can whip out here a minus 1. So we can factor this one out, and we wind up with minus 1 over square root of 2 of x 0 minus x state 1. So really, these two states just differ by a negative phase, right? And so we can just generalize this. Sorry, I'll write it out here so we can formally see. So when f of x equals 0, we wind up with x right here, x and state minus, because we can pull out the x and be left with x times 1 over square root of 2 state 0 minus state 1, which is minus. And if f of x is equal to 1, this x comes out of here, and we're left with minus state x state minus. So they have this generalized here by stating that depending on what the f of x is, -1 will be applied or not applied. So we have 0 and 1 as our powers. So we say -1 to the f of x, state x, state minus. So if f of x is 0, then this will equate to 1, and we will be left with just x, state minus. If this is 1, we'll be left with negative 1 to the first, which is just negative 1, and we will wind up with minus x state minus. So that's called phase kickback. Our original y that we turned into minus for the purposes of doing this remains the same, right? We stay in minus, but state x acquires a phase, a multiplier by the state, by the two states here, that varies depending on what the oracle outputs. So it says here that in notation they often just drop the answer qubit. So x, we would just write this generally as u of f x x, and it is a phase oracle where the effect of the oracle is to multiply the input qubit by some phase dependent on the value of x itself. And that will, I'm fairly confident that that is probably one of the most important things that we've covered so far, because that's huge in some of the algorithms. Let's just really quick take a look at 7.3 as an example, to work through an example with an oracle. So we have a input qubit x that is in superposition square root of 3 over 2 and 1/2 over 1, or 1/2 state 1. The answer qubit y is in state minus, right? So show that the quantum oracle acts by essentially we're passing our input and our answer qubit, and that this is the resulting output input qubit and answer qubit. So we can just work through that similarly to how as we did above, right? So the the u of f applied to x and y, or pardon me, x and minus, is equivalent to u of f of square root of 3 over 2, 0, plus 1/2 state 1, and state minus is unaffected over here. Or, sorry, it is, I need to rewrite that, my apologies. Over 1 over square root of 2, state 0 minus state 1. It's our minus in superposition form. Alright, so the U-gate is going to distribute through here. So we'll wind up with square root of 3 over 2 u of f state 0 plus plus 1/2 u of f 1 times our minus. I'm going to go back to rewriting this as minus because the U-gate does not touch this, I'm fairly certain. I might be wrong, I can go back and refactor that. But so the U-gate has the ability to assess a on 0. So 0 is our input, and f of x is the output of u of f and our input bit, right? So u of f maps this to maps 0, right? So f of 0, that's what it's doing inside the oracle. So what we wind up with is, since we know that the quantum oracle essentially results in this guy right here, right? Minus 1 f of x, x, what we would wind up with is square root of 3 over 2 minus 1 f of x, state 0, plus 1/2. So the u, the u gate applied to 1 is going to assess a phase depending on our value there to state 1, and this will all be multiplied by state minus, right? So now we know the value of x for each of these, right? Applying u of f to state 0, x is 0. So our final form, taking it from this general form to the specific form, is square root of 3 over 2 f of 0, state 0, plus 1/2 minus 1 f of 1, state 1, all multiplied by state minus. Is everyone good with that, or should I do I need to go back and, or are we good with 7.3? Okay, perfect. All right, so for example, in 7.4, we saw that when the answer qubit is in the state minus, we get phase kickback. Let us explore what happens if the answer qubit is in state plus. So suppose an input qubit and answer qubit are in the state x plus, where x is a bit. Apply the quantum oracle with same format there, maps y to f of x. So we will emulate what happened before. We'll do this longhand, so I'll write out plus instead of keeping it in plus form. So we have x and plus. We want to apply some phase oracle, u of f, that maps to x and y xor f of x. So let's first get everything written out and distributed here. So this is 1 over square root of 2, 0 plus 1. Distribute things through, we wind up with 1 over square root of 2 state x, state 0, plus state x, state 1. So make sure we're on the right track there. Yes, perfect. So the U gate gets applied here to this, and we wind up with 1 over square root of 2 and x and that's right, yeah, and 0 xor f of x plus x xor of 1 and f of x. Now we can rewrite this with our various f of x values. So when f of x is equal to 0, this will evaluate to 1 over square root of 2 x, and 0 xored with 0 is 0. So x state x, state 0 plus state x, and 1 XORed with 0 is 1. Similarly, when we have, Christ, I don't know why it's doing that. Okay, similarly when f of x is equal to 1, this will evaluate to 1 over square root of 2 x. 0 XORed with 1 is simply 1. So state x, state 1 plus state x, and 1 XORed with 0, or pardon me, 1 XORed with 1 is 0. So if we put y into, if we transform y into state plus, we actually don't get the phase kickback because we wind up with both of them being the same. We have for either well, that says for either, just take my word for it. For either f of x equals 0 or f of x equals 1, then we wind up with x, so we can factor both of these and pull out an x of plus, right? So we don't wind up with any type of phase kickback if y is set to plus instead of, and state plus instead of state minus. So yeah, so A is we wind up with x plus, B we wind up with state x, state plus, and the answer is C. How do our answers in parts B and A compare to the initial state? They compare to our initial state x plus by being identical. So the y bit remains the same, but the x bit also remains the same with no phase kickback. All right, the first of the problems that we talked about, what we're going to talk about, and building up to our first big algorithm solution is parity. Not, when you make fun of something, although I'm a big fan of parity as well. Parity with P-A-R-I-T-Y simply refers to whether the number of ones is even or odd. So if we have bit 0, we have bit 1, this is 0, this is 1. So parity would tell us whether or not there's an even or odd number of ones. So here we have an odd number of ones. So we have an oracle f of x that does this, and it takes an index x 0 or 1 and returns a corresponding bit. So in order to understand classically what's going on here, we would need to call it twice, because we would need to see what the value of B0 is. So, sorry, input is X membership in the set 0 and 1. So we would need to compare, we would need to call our oracle classically, get B of 0, call our oracle again, and get B of 1. And that way we could know what our values are, and thus how many ones. How many ones? Is it even or odd? So we want to know essentially what the form they put it in is an XOR, right? So if there's an odd number, we will get 1. If there's an even number, we'll get 0. They'll both be 1. We have an even number. If they're 0, we'll get 0. I'm not exactly sure how they handle that edge case, but the issue is that basically for every 2 bits, we have to call it twice. However, quantumly, that's a thing, quantumly? Oh yeah, they use that word. Quantumly, we only have to do it once. We query the oracle once. So like they were saying here, we would need to query b of 0. We would then need to query b of 1, and then we could XOR b0 and b1. This isn't part of the query complexity. So we would say here, this calling the oracle is. So this is the actual part that the oracle does. So the query complexity, we'll call it QC, is equal to 2. However, with Deutsch's algorithm, we can do it in one query, although I find it kind of sus. So Deutsch's algorithm, which is our first algorithm tackled, very exciting stuff, is an oracle that takes in an input qubit, an answer qubit, and pops out the parity. And we will build the circuit and then work through it like they do. So it's using a phase oracle. We can see that right away because they put our answer qubit into minus. So we know that when we are going to assess, we're going to use our oracle U, that there will be a phase kickback, and the answer qubit will remain the same. So they have two Hadamards that surround. Okay, very funny stuff. All right, get out of there. They have two Hadamards on either side of this, and for our input qubit. Then they measure, and we get our parity. So how does this work? So basically, we're going to use that phase kickback, the nature of phase kickback, to determine parity. So this oracle is in form, or pardon me, the output of the oracle is we worked on this one. We showed this one in the example above that we did. 0 plus minus 1 f of 1 minus 1 f of 1 state 1. So this is the effect of the our phase oracle. It will apply a phase to x, where we have our x's here. This is our input x, or rather the phase that's applied to that, and the we maintain the answer qubit. So let's do to show how this works. Let's say that f of 0 is equal to b of 0 using the same oracle setup that we have up here, right? So f of x, x is the index of the bit. So where x is 0 and 1, we're doing a 2-bit example here. So x of 0 is b sub 0, which would be, in this example up here, for example, 0. B, f of x would be b sub 1, which in this example up here would be 1. But so let's say that f of 0 equals b sub 0, and f of 1 equals b sub 1. So when we rewrite this into, when we replace this in the form that we have it up here, minus 1, so f sub 0 is equal to b sub 0, so we substitute b sub 0 in for f of 0, minus 1 b of 1, state 1. All right, now we can factor out a minus 1 b sub 0, leaving us with state 0 plus minus 1 b of 1 minus b sub 0 of state 1. And this tricked me up for a second when I first saw it, but because when we distribute this back through and we multiplied -1 to raise to the power of b sub 0 and this, we add the exponents, and basically this would remove the b sub 0 component, and we would be left with just b sub 1. So b sub 1 with a b sub 0 factored out is just equivalent to b sub 1 minus b sub 0, just because of the exponent rule. And so that allows us to pull this phase out. And so depending on if b0 and b1 are equal, then we wind up with -1 b sub 0 0 1 over square root of 2 0 plus 1, because if b sub 1 and b sub 0 are equal, then this exponent will evaluate to 0, which will cause this to be 0, and will give us just an amplitude there, or give us 1 there, and so we'll wind up with this. If b0 does not equal b sub 1, then we wind up with -1 b sub 0 1 over square root of 2, which is 0 minus 1. So for example, if for whatever reason, right, if b sub 1 is 1 and b sub 0 is 0, this will equate to 1. It'll give us -1 to the 1. If this is -1, or so if b sub 1 is 0 and b0 is 1, this will give us -1, which will just give us -1 to the negative first, which gives us 1 over -1, which gives us -1. And that's why we wind up with 0 minus state 0 minus state 1. So effectively, if b sub 0 equals b sub 1, we wind up with -1 b sub 0 plus, and if b sub 0 does not equal b sub 1, then we wind up with -1 b sub 0 minus. And we can distinguish what these are then by measure, for Christ's sake, by measuring in, if this would stop drawing lines whenever I click, if it would let me pan. Nope. All right, not going to let me pan. So all we have to do now is measure in the x basis, right? And if we, since an overall global phase does not affect a measurement outcome here, right? So because global phases are irrelevant to measurement outcomes when it's applied to the entire superposition. Now, if you apply a phase to one state in a superposition, yes, it will affect measurement. But global phases are irrelevant to measurement. So we could measure this in the x basis, and if we get plus, we know b0 and b1 are equal. If we get state minus, we know that b0 and b1 are not equal. So therefore, if not equal, parity is odd, right? Because if they're not equal, then we have either 0, 1, or 1, 0. We have an odd number of ones, so parity is odd. Otherwise, parity is even. They're both the same, so we have 2 1s or 2 0s. What they do is they take it a step further and they apply the Hadamard gate to this to this to our forms here. And when you apply the Hadamard gate, you wind up with, minus 1 b sub 0 Hadamard applied to plus, which gives us minus 1 b sub 0 0. And conversely for our minus, oh, why did I do the text box? Minus 1 b sub 0 Hadamard applied to our minus, we wind up with 1. And then we measure in the z basis. And if we get 0 or 1, that tells us which of these we are in, and which, if we get 0, we have even parity. If we measure in 1, we get odd. So as they stated in the lectures, this algorithm is basically useless. It only exists to show quantum supremacy in terms of query complexity, right? We made one call to the oracle and we got out our parity result. However, when I started really digging into it, I said, well, don't we need to know the value of the bits, right? The function has to query, or sorry, not query, I don't want to use that word twice. So within the oracle, within our oracle, we have to know the value of B0 and B1 to output our final result, right? So how is this more efficient than doing it classically, where we have to query twice to get the value of each of them, and then we XOR it, right? Well, it's one of those quantum things, right? Well, we say, well, we only have to query the whole thing once, and we get the result. So, it says, note in Deutsch's algorithm, we never learned the values of B0 or B1 themselves. Instead, we only learned if they're equal or opposite. I don't know about that. So let's see if there are any examples that are popping out. Yeah, I think that's, if everyone's good with Deutsch's algorithm, I think we can move on. Oh, now it's scrolling. Okay, now it's panning. Cool. All right, so to tie into the lab that we just did with Deutsch's algorithm, we can generalize this to additional bits. So we can, if we have a string of bits, or in bits, B0 to some arbitrary Bn. Classically, if we wanted to know all of them, we would need to do the entire sequence for n queries. But here we can just do it in n2 quote-unquote queries, because we take each pair and we slap it through, and then that's and then we take the XOR of all of the parities to get the overall parity. So let's say we have 6 bits here, so 0 1 1 1 and 0 1. So we would do 3 oracle queries, which would output put 1 0 and 1, and then we would XOR all these together. Since they're not all ones, we would wind up with 1, which tells us that we are even. Wait. That is incorrect. B of 0. Oh, let's see. Okay. Okay. Oh, yeah, yeah. So if we get 0, then we know that they're even. Oh, wait. My apologies. Yeah. Scratch that. All right. So constant versus balanced functions. Let's see. What is it? 710. I'm going to go for 20 minutes on this. And then at 7:30, I'm going to grab a 5-minute break, and then we'll go into the lab. Or the first lab, pardon me. We'll go to the first lab. Constant versus balanced. So we have, f of x that takes in some binary number of length n. Of the length n. It's got n minus 1, n minus 2, blah, 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 all the way to x0. And, we can rewrite this as a set of 0 and 1. And we additionally have the promise that that f is constant. F is constant, pardon me. Oh, I apologize. F of x either outputs 0 or 1. That's what f of x does. It outputs 0 or 1. So it's either constant, it are either always outputs 0, or it always outputs 1, or it's balanced. So it outputs 0 half the time, outputs 1, or outputs 1 half the time. So put another way, as they stated here, f outputs 1 either none of the time, all the time, or half the time. Same thing for 0, right? Or 0, none, all, or half time. So looking at this table that they have on 282, so we have a binary string of length 3, and the f of x is balanced because it's putting out 0 half the time. We've got 1, 2, 3, 4 zeros, 1, 2, 3, 4 ones. So the classical solution is to input half the solutions, or half the inputs, plus 1 in the worst case. So if, for example, we have a bit string of 6, of length of n equals 6, then let's say we put it in for, we've submitted the, we've put it in for, we put it in 3 times, and we've gotten 0 back from f, right? F has given us 0 so far. Now, if we need to do one more time to make sure, right? Because this is half of our input, so we still don't know if it's constant or balanced. Now, if we put it in for a 4th time, and we get 0, now we know that it's constant. It's always out inputting 0, because otherwise, if we see 1, we know that it's balanced. Because for half it gave us 0, and for the second half it's going to give us 1. So we always have to do half the inputs plus an extra, half of the input in, plus 1 queries. So if n is 6, we would have to do 4 queries, passing in our binary numbers of length 6 into our oracle, or our function, our classical function. So the quantum solution demonstrates a ridiculous speedup by using 1 query. Pretty crazy stuff. So this is it's an exponential speedup compared to classic. Because let's say that we have n is 100. Well, we know we're going to need 51 classical queries, so we only need 1. It's if we have 10,000 n, then we need 50,000, or pardon me, 5,001 queries. We only need 1. So it's exponential compared to our classical solution. So the Deutsch-Jozsa algorithm determines with 1 query. It kind of has as its base the Deutsches. Oh, it's with an S there. Deutsch-Jozsa. Okay. Now we have n qubits plus an answer qubit, which we ignore using a phase oracle. These n qubits are initially in 0 state, and then we use Hadamard, similar like we did in Deutsch's algorithm, to put them into superposition. We apply our UF gate, our U of F. So up here we have our minus. We have some arbitrary number of input qubits based on whatever the length n is of the binary number that we're trying to look at. And we put in, it has Hadamard gates for every input qubit. The gate does its thing, and then we Hadamard on every input qubit as it comes out, and then we measure all of our input qubits. So basically, mathematically, to understand how this works, right? So we have, we're gonna so they say to just ignore the answer qubit. So we have all these answer input qubits that start off in state 0, and we're going to, and this is just this is just notation that shows the shorthand form of writing out all these zeros in here. So we're going to apply a Hadamard gate to each of those. And each of the zeros is transformed, each of the 0 states is transformed into a plus state. So we have n, now we have, instead of having n 0 states, now we have n plus states. this is equal to 1 over square root of 2n, because each of these plus states has its own 1 square root of 2, 1, etc. So when all these are multiplied together, we can generalize this as saying 1 over 2 to the nth power. Now we can, so rewriting this, we've got 1 over 2 to the n, 0 plus 1 n times this superposition. And rewriting that further, we have 1 over 2 to the nth power, or 1 over square root of 2 to the nth power, times the sum of the state x, x being a member of this set. So I know the notation is a little bit awkward. Is everyone kind of does everyone kind of clear on how we jump from here to here? Okay. So the next step is that we're going to apply a Hadamard. Sorry, hang on, let me erase here. The next step after that is the phase oracle. So basically, when we did this, it created a uniform superposition over all the binary strings. So we apply the UFF gate. We wind up with an sum of x and basically, yeah, this again is just the set notation saying that for every x, it's a member of the set 0 or n that occurs n times. So it'll be a 0 or n. There's this big set that has 0 or n, these pairs occurring n times, and for each x, it's an individual, it's a member of that little subset of that. So sum, and when we apply our u sub f gate to that, we wind up with 1 over 2n some thingy x membership of 0, 1, n. And we know that when we apply a phase oracle to, much like in Deutsch's that we did, so this is U of f is a phase oracle, just like in Deutsch's algorithm. So we know that it will apply a phase concurrent with -1 f of x to state x. So that is our output after we run the oracle on it. There's phase kickback, and we have this phase applied to our input qubit. So next, we're going to apply the Hadamard again. So we'll take this state, and we'll apply a Hadamard to every output that came out of this, every answer qubit that came out here that has a phase kickback applied to it. So, and we wind up with 1 over square root of 2n x member of 0, 1, n -1 f of x h n times to state x. So this is the final form of the final mathematical form before measurement. And so we're going to zoom in on 1x, example of x, where x is just a single n-bit string, pardon me. So when we're applying h n to x, let's say so x is an n-bit string. So we have the outcome is h. We can rewrite this as xn minus 1, xn minus 2, all the way to x0. And basically, when we apply the Hadamard, it's going to apply to each and every one of these. So we have h of xn minus 1, h of xn minus 2, dot, 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 h of x0. And depending on whether xi is 0 or 1, then h of xi is either plus or minus. Oh, I see. Yeah, my apologies. So basically, because 0 or 1, Hadamard on 0, whatever this x, it kind of messed me up a little bit when they switched over to xi, but each of these is just a general xi, right? That's just how we denote whatever one we're on here. x1, xi is just the general term there. So if xi is 0, then the Hadamard applied to that will be a plus state, and if it's equal to 1, then it will be a minus state. So we can rewrite that as saying h of xi is equal to 1 over square root of 2, 0 plus minus 1 raised to the power of xi, state 1. So this is the general form of each one of these here. So depending on xi, just like we saw with the phase kickback earlier in those examples, we will either assess a phase, either one will have a phase or it will not, depending on the value of xi being 0 or 1 in our binary number string. So it will either equate to plus or minus depending on the value of x. So obviously we have a gigantic sequence of all those. For all of the x's, I won't write this out by hand, but we put all those together, substituting the x that we're in, the x that we are on for the exponent, and through distribution, etc., and simplification, we get the final form here. So when we are distributing through, we add exponents like this. Then we wind up with, this long thing here. And maybe it would help to do this as an example. Let's say that we have a string that is that has length, that it's n equals 3. So let's say this is our binary number, 101. It's with 3 bits. So the Hadamard applied to that would be, we would wind up with 1 over 2 square root of 2n times, so for x is equal to n minus 1, which so position 2 here, x is 1, so we would wind up with 0 plus minus 1, 1, state 1, So, and these are all products, right? So 1 over square root of 2, 0 plus minus 1, and right here we have 0 times state 1 times 1 over square root of 2 1 over square root of 2 of 0 plus minus 1 over to the first, state 1. And we wind up with, we'll pull out all these 1 over square root of 2's. We'll call it 1 over 2 square root of 1 over square root of 2 to the third power of, and let's figure out what we have here. So state 0, minus 1 to the first is minus 1, so we have minus state 1 times 0, minus 1 to the 0th power is 1, so we have plus state 1, and again here minus 1 to the first is minus 1, so 0 minus 1. We can distribute through in this example. I'll do the first two first here. So we know 0, 0 minus 1, 0 minus 1, 0 plus 0, 1 minus 1, 1. Multiply this guy through by 0 minus 1. Take the 0 through first. We wind up with 1 over, I'll just write it as 1 over 8, so 1 over, pardon me, square root of 8, which is, actually it just simplifies even further to 2 square root of 2. 2 square root of 2. So 0 coming through from the right term here and just distributing along all of these gives us 0, 0, 0 minus 1, 0, 0 plus 0, 1, 0 minus 1, 1, 0. Bringing our minus 1 over and distributing it through, we get minus 0, 0, 1 plus state 1, 0, 1 minus 0, 1, 1 plus 1, 1, 1. So we wind up with an equal superposition of these three strings, all with amplitude 1 over 2 square root of 2, which is equivalent to 1/8 when we take our norm square. So we wind up in this big superposition, and they've got it written here in some form. So we have, they generalize this out to 1 over 2n, square root of 2n, multiplied by the sum of z being a member of 0 and 1, nth, minus 1 raised to the power of the sum of I colon zi equals 1. What in the xi state z? Okay. So for the negative sign, this power is the sum of all values of xi such that z of I equals 1. So Z is brought in to show the... I'm losing it with Z a little bit, honestly. Oh, we move from X to Z here. XI. This to 1XI. Oh, I see. Okay. So basically, what they're saying is we have here, so the powers that are here that determined whether we went positive or negative for these various ones over here. This is just, each of these is represented as a sum, or if there's a negative one, an imaginary negative one in front of here, that is represented by the sum of the various x's that went to compose it. So like if, I forget which indexes came from which one, but basically there's a -1 here in front of all these, and its exponent is the combining values of x that went to determine whether it be negative or positive, much like they have here. And that's what is represented by Z. Oh, I see. All right. Gotcha. Okay. So Z, state Z is just it's a replication of x, the original x, to demonstrate that what we have is the sum. We have all of our bit strings here. So Z is our individual bits in our bit string. And we're taking the sum of all those bit strings contributions to the -1 to the power that we were raised to, and the bit strings themselves. That's what I'm evaluating this as. This notation is pretty funky, so I'm not mathematically inclined enough to really get what I colon Z sub I equals 1 raised to the power of xi state Z is really asking me here, but that's what I'm taking it as. Basically, so for the negative sign, the power is the sum of the values such that xi such that zi equals 1. And we can also write this product using the sum. We're using the dot product. So in the dot product, the only xi's that survive are those where zi is 1. Otherwise, where zi is equal to 0, then this will equal 0. So for wherever z of I is 0 in the dot product of x and z, xi disappears, and we're left with only the xi's where z of I is equal to 1. Oh, okay, I see. Down here it's clarified. I just got stuck on that one up there. So here they clarify. Basically, we've walked a very long road to get to this point, but the tensor product of h n times applied to our x's, where x is our bit string, is equivalent to 1 over 2 to the nth, the sum of z 0 1 n minus 1 the dot product of x and z times state z. Okay, so z is a copy of x, and so wherever x and z would be 0, or I guess x, but then we take their dot product, and we take the dot product, and where it is 0, it cancels out, and we're left only with the ones. And so then we take the sum of these, all the states, and yeah, okay, I get it. Then you plug it in, you measure it. Plugging this into equation 7.2, which was where? 7.2 was where? Ah, okay. So we'll go back up to our original 7.2 equation here. Plug this bad boy in into where H tensor product in state X is. So we wind up with what's going on? Okay. We plug this back in to our original equation. So X member 0, 1, N minus 1 f of x times 1 or 2 square roots of n of this new thing that we've discovered here, minus 1 dot product of x and z. And this simplifies to, we can distribute that through. Now I don't necessarily, I hate it when they leave out intermediate steps because I don't necessarily understand how they get the final form here. So I understand that this, that the input, the two 1 over 2 square roots, 1 over square root of 2 to the power of n's, this one will come over, creating 1 over 2n. But how are they? I'm not exactly sure what's going on with the summations. Mm-hmm. Okay. Oh, I see. Okay, I see what you're saying now. So basically, what they do is they combine. Okay, it's gotcha. Summation rules. It's been a while. So we move the z summation out to the exterior, and then you're right. The x term, the x sum, moves in because we have minus 1 f of x. We have minus 1 x dot product z, and so we take this and we combine the two here. So minus 1 f of x plus x dot product z state z. Okay, cool. So how the hell does this allow us to determine if a function is constant or balanced? So we can calculate the probability of getting all zeros. So the amplitude of 0 right before measurement is 1 over 2n root of x n minus 1 to the f of x. So this winds up, this amplitude depends on whether or not the f of x is constant or balanced. So if f of x is constant, then it always outputs the same value for all x, and the amplitude is 1 over 2n summation of, blah, 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 we won't write that out again, minus 1 of f of all zeros, because we're looking at the probability of getting all zeros. So minus 1 f with our string there, and our amplitude winds up being 1 over 2 to the n minus 1, oh, sorry, minus 1 f of 0, 0 times 2n, which winds up negative 1 f of all zeros. If we take the norm square of this, then if f of x is in fact constant, if we get all zeros, then the probability is 1. Because for every 0 that we get, we would get 1, right? And if it is balanced, then we would get 0 as the amplitude. So if it's balanced, then minus 1 raised to the power of f of x is 1/2 the time, and minus 1 the other half the time. Oh, I get it. Yeah. Man, I'm loving this review. God, this is driving home crap that I really didn't get the first time. Mathematically, at least. I did things in code, but not math. Yeah, so we measure, and then if we get, if it's constant, we'll get 1. This will always equate. This amplitude will always equate to 1. Otherwise, it'll be 1/2 the time and minus 1/2 the time, which will give us an amplitude of 0. And yeah, nice. Got it. All right. So we know if when we measure, if we get 0, it is balanced. If we get 0, or if we get 1, then it is constant. Oh, sorry. If we get zeros, if we get all zeros, pardon me, then we know it's constant. Jesus, it is constant. If we get something else, the function is balanced. Because if the function is all zeros, then the probability of measuring, okay, yeah, this is all gluing it together for me now. If the function, where did that go? Okay, function is constant, then when we measure when we do our final qubit measure, this will be 1. Where we take the norm square of the amplitude using this phase. The phase is the amplitude in this case. This will equal 1. So if we get 0, 0, 0, if we get all zeros, then the function is constant, because the probability of measuring all zeros was 1. Otherwise, it's balanced. is that means that at some point it did not measure a 0 in there. It measured a 1. And because we know that it's either constant or it measures a 0 or a 1 half the time, right? It's 50% 0 and 50% 1. The fact that we got anything other than 0, 0, 0 tells us that it's balanced, because the way that it's set up is that the amplitude of, when it checks the amplitude of a balanced state, we get the probability of 0 for 0, 0, 0. So it's either 0 for all zeros, or it's 1 for all zeros, the way that this measurement is system is set up. Got it. Oh, I see. Yeah. Okay. Understood. That one's a pretty funky one mathematically. Um, it was that was definitely a brain teaser. um, Before we grab a 5-minute break, does anyone have any questions about this? I know I'm still kind of a little fuzzy on some of the notational stuff that they do, but I think I get the general idea of what they're doing. But does anyone have a question? Yes. So that is, so it's the way that the sum unravels. So they basically, so we have the sum of 2 over n, or sorry, not the sum, 1 over 2 over n, sum of x, 0, 1, n, minus 1 of f, all zeros. And when we think about that sum, right, this sum is going to occur 2n times, because this is basically the same thing as saying 1f all zeros times 2n, because there are two n iterations in this. That's what I'm taking it to mean as, right? So it's plus minus 1. So if we have n is equal to 3, let's say we have a 3, like the earlier example, we have a 3-bit number, then when we expanded it out, we saw a superposition of 3 qubit states. We saw an 8 state superposition. Let me see if I can bring that up. Good. Yes, yeah. So, and each of those superpositions has each of those superpositions in the 8-state superposition, it has a phase that has this. It has the minus 1 f of x there. And so we generalized, through their various black magic here, they generalized down to this, but this occurs 2n times, 8 times. So in the case of the 3-bit, we would have 8, and this would be, the amplitude for each of those would be 1/8, and then this would cancel out, and we would be left with just the raw phase that goes for each of those superpositions. So that's what I'm still slightly fuzzy on, where is it? Hmm. For example, if what if f it's all ones, you know? I think that regardless of whether, so if we have a bit string that is all zeros or all ones, it should evaluate through this metric to be to give us a probability of 1 for all zeros, right? I think that's what this is, that this is what this is set up, all this, the way that it's mathematically set up to do is that if it keeps encountering, then it sets this position, this probability of this superposition to 1 in the final measurement for before the final measurement, when the oracle operates and it goes through, we wind up with a superposition where if the n-bit string gets passed through, it goes into it goes through our oracle f, and if n is constant, if the function output, if the oracle f of x, pardon me, not function, the oracle outputs constantly, then regardless of whether it's 0 or 1, the final superposition will have an amplitude of 1 for all zeros, and if it's balanced, then it'll be 0. So when we measure, if we get all zeros, then we know it's constant. Anything else, we know it's balanced. I think we pardon me. They so the example they used was zeros, and I assume that we can expand that example just to do the same thing but with all ones, you know, because if they're all ones, we would have the same result. So if we measure and we get, so basically we pass in our string, and we could just expand that to say if we get all zeros, a state that is all zeros or ones, constant. And if we get any other state that's like 1 1 0 or 1 0, right, some combination of those, right, then we know that it is balanced, because this mechanism mathematically causes the probability of 0 0 0, what are all zeros or all ones in this case, to be 0. That's my understanding. Yeah. Now, I don't know, because the thing is, the superposition, okay, the superposition also, okay, actually no, it's just zeros, it's just all zeros. Because if we think about it, right, the superposition that we create, like we created with our 3-bit sequence, with our 3-bit length, our 3-bit string, that superposition also, it contains all zeros here, right? But it also contains all ones. And so each of these has obviously their phase in front of it. And so the mechanism that I believe that's working is that as our string is, as our function, our oracle function, pardon me, function. I don't want to say parses. Well, fuck it. Let's say parses our string. And, outputs some f of x. If every f of x is the same, if the phase x is the same for each input, pardon me, the resulting superposition of strings, because basically the superposition is just every combination of the 3 bits, right? 0, 0, 1, 1, etc., right? So 0, 0, 0, it represents every possible, sorry, what am I doing here? 2 to the nth. So we have a 3-bit, we have 8 possible superpositions representing every 8 possible 3 n-bit string that can be made from 3 bits. And so as it goes through, the resulting 0, 0, 0 state, let's say in our 3 n-bit string, will be 1. I feel like I need to go back through this math again, but I don't necessarily know if we need to understand everything on, like, they kind of lost me when they brought Z in just a little bit. Like, I grasp like what they're doing. I wish they had discussed a little bit more detail in this last part here of the algorithm discussion, what the hell is going on. But yeah, it's I believe that every single, let me just, you know what, I don't want to talk out of my, southern end. Let me just Google this really quick. In Deutsches. Let me just look at the Wikipedia. Deutsch. Okay. Mm-hmm. Oh, okay. Yeah, so it is. So it is only. It says, yeah. So on the Wikipedia, they've got so the probability. This is from the exact wording here of measuring. Well, they have k equal. They're using k, so I'll just use z. So of measuring z equal. So like we had in our example, the probability of measuring z equals 0 corresponding to 0 tensor product n. So 0 is for all the length of n, the input binary string, is the norm square of 1 over 2 square roots of n, sum of x is 0 to 2n minus 1 f of x. Gotcha. So which evaluates. So just from x is 0 to 2n minus 1, so that would be the total. Let's see, 2n minus 1. Oh, 2 to the nth, pardon me. Oh, I took everything out. 2n minus 1. Okay, there we go. That's a summation. So basically, the sum of the phase kickbacks, the phase, for every x for, and this is, as we know, the sum of all the various x values that have made up that superposition. So when we did our cross multiplication, basically they were saying that you have one f of x. This part might be composed of like x1 and x sub 3 plus x sub 0, whatever, like depending on the way that things have been distributed around to make the superposition. And so we do that for x is equals 0 to 2n minus 1, which is for every state in the superposition. We are adding up the phase, adding the phase. The phase is controlled by the values of x that went in. The exponent is controlled by the values of x that went in to create it during our distributive process when we were creating the superpositions. And then that all determines whether this is 1 or negative 1. So basically, if it all equates, so if it equates to 1 half the time and negative 1 half the time, then we wind up with this being, this norm square of this being equal to 0. But if this is always 0, then we wind up with, this is always 0, no, and my apologies. This would, if this is always 1 or negative 1, I guess you could say. No, I'm sorry, I'm confusing myself and I'm probably confusing you guys too. Basically, f of x minus 1 to f of x is either going to all the time be minus 1, or all the time be 1, or half the time be 1 and 1, or 1 and minus 1. So since we're taking the absolute value here, if a function puts out all ones, right? If the function puts out all ones, then this will be minus 1. And it'll be all the minus ones added up for every superposition that we have, right? So 2 to the n. And then, but they'll be added up 2 to the n times, right? So because this is equivalent to 1 over 2 to the nth sum, or not sum, minus 1 f of x to n. That's what the sum part is equivalent to. And then we just divide it by the number of times that it was done. These would cancel out, and we would basically just be left with this, which is either 1 when we square it. That's either going to be 1 or 0. Because if it's 0, that means that we've had an equal amount of 1s and negative 1s. So the whole idea with which it appears the secret, well, let's call it the secret sauce, is that for some n-bit string, n-bit binary string, if we measure and we get 0 to the nth, we get the state of 0 n times, so 0, 0, 0 for n equals 3, etc. then we know that it's constant because the amplitude, which is calculated by this sum here, this minus one, or yeah, this right here, gives us the probability of being in all zeros, of getting a state of all zeros. And if it's constant, this will be because the amplitude for all zeros is set to 1 when f of x is constant. And otherwise, it's set the amplitude of all zeros to 0. So we know that, for example, if we measure and we get some other state that's not zero, all zeros, it's not just well, we were in a superposition and we measured, so maybe there was a chance we could. No, the way that it's set up is that either there's a 100% chance of getting all zeros, or there's a 0 chance of getting all zeros, and depending on what we see, we know whether it's constant or balanced. Whew, that was a trip through space time itself, man. What time is it? It's 8:15. I'm gonna grab a 5-minute break. Rest the eyes, um, and I'll be back at 10:17 Eastern. All right. 4. Now let's check 5, whichever one we're on now. 7.1a. The truth table is okay, perfect. And this is x and yx, or f of x. And this is where f of x equals not x. Mm-hmm. Mm-hmm. Oh, okay, I gotcha. Oh, oh, I gotcha. Mm-hmm. Oh, okay. Yeah, I understand. So, sorry, 1. So we have. I see. Yeah, I didn't. I honestly didn't even make that connection. 0, 0, 1, 0, 0, 0. I was. I mean, I typically the. I was thinking about it in terms of the matrix operations. You know, the yeah, the tensor product of x and I, because since f of x evaluates to, if f of x evaluates to uh, not x, then we can use an x gate for that. And then I was using an identity gate on, and I'm pretty sure I think it gave us the same answer. So mm-hmm. Oh, I see, because this is this is I tensor product x, and x tensor product is 0, 0, 1, 0. Neither of these two are what we're looking for. Oh, okay, I gotcha. So, okay, yeah, no worries. Well, cool. Now we can, well, because we didn't, because I used the wrong matrix, pardon me, to calculate unitary. I'll just use our correct matrix now to do the part C, or part D really quickly. We know it's reversible. The truth table tells us it's reversible for B. We have the quantum oracle in matrix form now, thanks to you. And we can just do a unitary operation. So 0, 1, 0, 0. and multiply it by its conjugate transpose, which we don't have to do the conjugate part, but we do need to transpose it. Every row becomes a column. There's 0. Yes, okay. And when we multiply these together, I'll just do it with longhand instead of using the calculator. We get so for here, well, what we're looking for is the identity. So we want all these to be 1. So is row times column. So 0, 0, 1, 1, 0, 0, 1. Everything else would be 0. That is 1 here. This column, this row times this column. 1. And indeed, all the rest are zeros. Okay. Yeah. Cool. No, that's I had not even considered. I wonder if so. Hang on. What is so if we because I'm it's bugging me about like doing it in X, right, and doing it in matrix form. So we have an X gate, which is f of X, and then we are XORing that output with Y. So I wonder, what is the quantum XOR? Do the part C, part D really quickly. We know it's reversible. The truth table tells us it's reversible for B. We have the quantum oracle in matrix form now, thanks to you. And we can just do a unitary operation. So 0, 1, 0, 0. And multiply it by its conjugate transpose, which we don't have to do the conjugate part, but we do need to transpose it. Every row becomes a column. There's 0. Yes, okay. And when we multiply these together, I'll just do it with longhand instead of using the calculator. We get so for here, well, what we're looking for is the identity. So we want all these to be 1. So is row times column. So 0, 0, 1, 1, 0, 0, 1. Everything else would be 0. That is 1 here. This column, this row times this column. 1. And indeed, all the rest are zeros. Okay. Yeah. Cool. No, that's I had not even considered. I wonder if so. Hang on. What is so if we because I'm it's bugging me about like doing it in X, right, and doing it in matrix form. So we have an X gate, which is f of X, and then we are XORing that output with Y. So I wonder, what is the quantum XOR gate in matrix form? I wonder if there's a way to get to it. Quantum XOR. Let me. Oh yeah, it's a C naught. Yeah, you're right. So for quantum XOR is a C naught. Okay. So we have so X comes in, it performs an X on so we have an X gate on the input X, and then we have a C naught conditioned on, oh wait, hang on, C naught, there it is, of the X gate on operating on X, our input X, and with target Y. So to put that into matrix form, we could literally just do it in matrix form and see how that went, if like to go through the sequence. So we have X on X. So X can be either 0 or 1. So wait, we know what the X gate is. My apologies. X gate is 0, 1, 1, 0. And then the C naught of that with Y as a target is the C naught matrix. C naught matrix is what? Where are you? Oh, it's a 4 by 4, which is 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, and that's our C. That's the C naught, and we need to apply. Let me. Of 8. Yes. So matrix form of the quantum gate. I'm just gonna ask. I'm gonna ask Claude. Might as well. What is the matrix form of the quantum gate? C naught X of state X, state Y. State Y. Okay. And hopefully it's seen this before in its training, because they sure as hell can't generalize. So. Oh. Okay. I got it. So this is it says that this really is equivalent to the reverse C naught. Where if the original, so basically if the original X, the original C naught, or the reverse C naught, or the, I'm not going to write that out, or the controlled X with negative control. So if the original input is 0, it will flip the target. What's going on here? And the matrix form that they have written here is completely different to what the textbook says is the answer. So I'm not going to waste any more brain power on that one. The truth table can operate as the, you know what? Let's just do a quick screenshot of this and throw it in there. Pictures, screenshots. Solve and show steps. All right, so do they get the truth table correct? Let's see. Yes, they have the correct. Claude managed to find the correct truth table. That's exciting. Oh, okay. Oh, I got it. Okay. So yeah, what you were saying is exactly is correct. So basically, the originally we have 0, 0, 0, 1, 1, 0, and 1, 1 in our matrix, but then after it passes through the gate, these are swapped around through the gate. So, for example, 0, 0, 0, 0 becomes 0, 1. 0, 1 becomes 0, 0. 1, 0 becomes wait a second, what is going on? Okay, Claude needs to learn how to do a little bit of space here. Okay. One zero zero. Okay, 0, 0 becomes 0, 1, and 0, 1 becomes 0, 0. So oh Lord. Yes. Okay. 1, 0, 0, 0, and then these just stay the same. Yes. Okay. No, that makes sense. It's the matrix just represents the mapping of the states of one state to another state. I'm sure there's a matrix form for this specific gate sequence, but that's how would I implement this Oracle function step by step as a matrix? It just bothers me that I can't understand the Gotcha. Hmm. Okay. Yeah, no, that's exactly they. When I asked for a step-by-step way to make the matrix, it broke it down exactly like that again. So we just swap around the column vectors to their new locations that the Oracle maps them to. Okay. Well, thank you for bringing that one back up. That actually really helped me help clarify what was going on there. Um, yeah. No, I will. I think I'm still recording. Shit. Well, I'll have to edit this video and cut out the parts where I went over the lab and stuff, and then I'll post this on YouTube tonight for those who want to review. Yeah, I'm gonna go ahead and jump off here. We'll meet again tomorrow at 6 p.m. Eastern. 6 p.m. Eastern. We'll run. It'll be another 5-hour session because I'm really trying to get through as many of the big algos as I can tomorrow. Saturday, same thing, 6 p.m. Eastern. And then Sunday, if there's interest, we can do a session from 10 Eastern until noon. Like no textbook, just no like rote review, just random questions, right? Like any last minute things that we can kind of help each other understand. I'll put this all into the Discord stream. Put all this into the Discord channel. But thanks everyone for joining me. I'll see you guys tomorrow at 6 p.m. Eastern. Goodbye.